So the next section here is going to be transformation of functions. Now, before we can even really focus on transformations, we have to understand the basic functions that exist. So there are 6 basic functions that we should have memorized, or we should be able to recognize if they're plotted in front of us. So the first is going to be a linear relationship, okay? The second, I'm going from left to right. So the second is going to be quadratic, all right? And I'm giving you like little examples of where these functions are actually used. So linear, relationships, quadratic, vertical motion, path of flying objects. Absolute value would be distance, okay? Exponential would be population or monetary growth. Also decay, like half-life and stuff like that. Then we have a square root, which would be like diameters and everything like that. And then finally, cubic, which is volume relations. Regardless of what we have here, you got to be able to recognize that each one of these functions is very special. Okay? And and you got to know their graphs accordingly. So if you know the basic family of function that it occurs in, then you're going to understand the transformations very quickly. All right? So let me go ahead, let me get out a marker here, because the first type of translation that we're going to focus on is going to be a vertical shift. So suppose c is greater than 0, and we have 2 different types of shifts. So the first one, we have y equals f of x plus c, and then we have y equals f of x minus c. The f of x stands for one of those 6 family functions. So, for example here, if I have y equals, let's say x squared plus 1, well, we know first that the parent function is x squared, so it's going to be a parabola, and we just shifted up vertically 1 unit because the plus c is on the outside of the function. You're going to hear me refer to that. All right, so it's going to be on the outside of the function. Likewise, the second example here, if we have, we'll use function notation on this one. H of x equals the square root of x minus 1. Well, then I know all that's going to happen here. It's going to be the parent function, which is the root, and I just shift it down 1 unit. I put a dot, and then just let it increase very slowly, but it still increases. Now, the next type of translation, or the next type of shift we're going to be looking at, would be a horizontal shift. Here's our horizontal shift. Now, notice here, and this one, you really got to be careful with it, okay? Because we're going to suppose c is greater than 0, and what we're looking at is just the value of c. So, if you have y equals f of x minus c, you're going to shift the graph to the right c units, and then if you have plus c, you're going to shift it to the left c units. So, an easy example would be something like this. So let's say we have f of x equals the quantity x plus 1 to the second power. Now with this, I'm actually going to plot a couple points because I want you to see how this works. All right, so we're going to do, let's do -2, -1, 0, 1, and 2. So we'll plot 5 points because it'll really drive the point home. I guess pun intended there. I don't know. Anyways. So if I let x equal -2, then we're going to get -2 plus 1 squared, which is going to be, what's that? -1 to the second, which is +1. All right. Now, I'm just going to erase. We're going to substitute in -1. So -1 plus 1 is going to be 0, and 0 to the second power is 0. Okay. Now we're going to do 0. So this is going to be 0 plus 1 to the second power, which is just 1 to the second power. So this is going to be 1. All right. Now we have f of 1, which is going to be 1 plus 1 squared, which is 2 squared, which we all know that's 4. And then finally, we're going to do f of 2, which is going to be 2 plus 1 squared, which is equal to 3 squared, which is going to be 9. So now, if I were to graph these points, and I'm not going to be really particular with this. All right, we have -2, 1. So this would be like right here. Negative 1, 0 is right there. 0, comma 1 is right here. 1, comma 4 would be all the way up here. And then 2, comma 9 is going to be like all the way up here. But regardless, I think you get the idea that what we've done is we've shifted our parent function. Remember, that parent function, I'm going to write it in red, would have been right here. So what we did is we took this vertex and we shifted it 1 unit to the left, all right? Which is exactly what we would expect based off, and I'm going to highlight it here in blue, based off this part of the horizontal shift. So remember, if it's f of x plus c and your shift is actually inside of the function or inside of the parent function, that's a horizontal shift from left to right. All you have to do is just pay attention and think about it. If it's plus c, you're shifting to the left. If it's minus c, you're shifting to the right. Personally, I would be making flashcards with this stuff on it, with this information. Because remember, studying math is not doing a bunch of problems. Studying math is knowing this right here. If you know that, it doesn't matter what parent function I give you, you know it's going to be a horizontal shift. So real quick, just to show you a couple examples. All right. We're going to graph f of x equals the absolute value of x minus 4 plus 2. So the easiest way to approach this would be to first identify the parent function. So in this case, our parent function is going to be the absolute value, okay? 2. Let's do our horizontal shift. Well, since this is minus 4, we're going to shift 4 units to the right. And then finally, the vertical shift. And this will be shift up, or shift 2 units, we'll say up. Okay? So what I'm going to do first, in red, very lightly, there's our parent function in red. And then I'm going to take that vertex right there. Actually, it's called a cusp. You really learned a lot about that in calculus class. But we're going to take that cusp, and what we're going to do is we're going to take our attention, put it there, and we're going to shift this 4 units to the right, and then 2 units up. So 1, 2, 3, 4. And then we go up 2 units, and in black, there's that cusp, and there is our new absolute value graph. So that's how this works. You identify the parent function, think about horizontal and vertical shifts, and then go ahead and graph accordingly. Desmos, excellent at this. If you just want to graph the parent function, and then you want to go ahead and transition over to the new function that you have. So now that we're getting into this, I want to give us some steps, because the next types of translations we're going to be looking at are going to be reflections, and then compressions and stretching, okay? So it's always good to kind of have like a game plan on how to do this. So there are 5 steps. Get out the proper marker here. So we got 5 steps to graph a function or function transformations. All right, step 1. You always want to identify the parent function. Okay. Step 2. Reflect over the x-axis or y-axis. 3. This is where you're going to do your shifts. All right, this is either going to be vertical or horizontal. And then 4, you're going to look for vertical and horizontal translations. And then finally, step 5. You can just plug in a couple of your coordinates, or just plug in a couple of points. Into the parent function to double check. Personally, what I would probably do is just make sure if you want to, you can use Desmos to just check your work and everything, okay? But here are the 5 steps to graph function transformations, all right? Because like I said, we're going to start doing reflections now, and then we're going to end up with the vertical and horizontal translations, stretching, compression, shrinking, stuff like that. So we want to make sure we have at least some sort of a method on how to do this. Now, when we talk about reflecting graphs, you want to take very careful notice of where does that negative sign appear. So if the negative sign is on the outside of the parent function, you will reflect the x-axis. So this would be like the very first picture right here. So this is a reflection about the x axis. Now, the second picture demonstrates the second type of reflection. Notice that the negative is inside of the parent function. Okay, I'll zoom in so you can see it more. So notice that the negative is inside the parent function. So this will be a reflection in the y-axis. So notice how you have this blue line right here that I'm highlighting. Now it just flips over the y-axis. So this is a reflection about the y-axis. Okay, so I'm going to go ahead and just do an example here for us. Now, to keep things nice and neat, because like I said, I'm no artist, I'm just going to go ahead and use Desmos for this. But what I'll do is I'll show you the points that we have, okay? So we're going to keep it simple. We're just going to do the square root of x. So first, here's our square root of x. All right, now, if I want to reflect this about the x-axis, I put the negative out front. And notice that by putting the negative out front, I now reflect about the x-axis. Also notice, and I'm going to go ahead and just change a couple of these points here. So let's make this 0, 1, 2, 4, and 9. There we go. So notice that all your y values now change, which would make sense because you're reflecting about the x-axis, so all your y values are now negative, okay? Now, we're going to go ahead and let's just reset this. Remember, here's our parent function right here, square root of x. But now, I'm going to reflect this about the y-axis, which means the negative has to be inside of the parent function. So it has to be underneath the square root symbol. And when I do that, notice that it reflects it about the y-axis, which if you're thinking about it, then all of your x values have to change. So if I just go ahead and click on this, and I'm just going to go ahead and go negative 16, negative 9, negative 4. Oops, sorry. 16. This would be negative 9, negative 4, 0, and 1 will be undefined because it can have a negative underneath. So notice how this worked out for us, okay? So you got to make sure, like I said, where does that negative symbol occur? We'll tell you, do you have a reflection about the x or the y-axis, respectively. Now, with vertical stretching and shrinking, first, remember, vertical means the y-axis. Okay, that's what's happening here. All right? We need to be really careful because first, if C is greater than 1, you're going to stretch vertically by a factor of C. Now, if C is in between 0 and 1, so in other words, it's a fraction, okay? Then we're going to shrink vertically by a factor of C. So what I think the best thing to do here in this example is to just do points, all right? And then what I can do is later is I'll graph it, okay? So here's our first example. So let's go ahead and let's do, we'll do 2x squared. So here are x values. Here's the f of x equals 2x squared. In fact, you know what? Let me do this. F of x squared will be our parent function. And then in black, I will write the function that is going to be, in this case, this will be stretched vertically by a factor of 2. So pick some x values. Let's do -2, 0, and 2. Now, for the parent function, the quantity, -2 to the second, is going to be 4. 0 to the second is 0. 2 to the second is 4 as well. Now, notice here, we're going to be stretching this vertically, okay? Which means it's going to get, as x goes left to right, our y values are going to get bigger, faster by a factor of 2. So we're stretching that graph. So we have -2 squared, which is going to be positive 4, and then 4 times 2 is 8. Here we still have 0, and then we have 8 again. So notice times 2, times 2, times 2, we're stretching this graph vertically by a factor of 2. All right? Now what I'll do here is I'm going to do basically the same exact example, except we're going to make this a fraction, so we know we're going to be shrinking this graph by vertically by a factor of 1/2. So all my x value or all my y values now are going to get real small very quickly. So once again, here's our parent function. And I'm just going to keep everything the same. Let me zoom out here just a little bit. I'll keep everything the same just to make it very nice and neat. All right, so we got -2, 0, and 2. We have 4, 0, and 4. That doesn't change. But now this will. So we have quantity -2 to the second, which is going to be 4. But then 4 times 1/2 is 2. 0 and 2 again. So notice we're still multiplying, but now we're multiplying by 1/2 in each case. Okay? So I hope that makes sense. The last one we're going to be talking about, here we have horizontal shrinking and stretching of graphs. So once again, we're really going to be concerned about this letter C, but in this case, the C will be inside of the function. I'll zoom in for us. So it's inside of the function. And we know that if C is greater than 1, then we shrink horizontally by a factor of 1/C. And if C is in between 0 and 1, then we're going to stretch horizontally by a factor of 1/C. And once again, I think the easiest thing to do here is to plot points. So, let me see, what parent function? Let's do the absolute value again. So we'll do absolute value of 1/2 x. So we have x. Then we have our parent function here. All right. And then we have our function here itself. All right, so we have -2, 0, and 2. Now for the parent function, We substitute in -2, so that's going to be +2, 0, and 2. Now for our translated function, we have 1/2. So it's going to be -2 times 1/2, which is going to be -1. And the absolute value of -1 is 1. Then we have 0. And then we're going to have 1 again. But notice, let me get out my highlighter here. Our C value is 1/2, which is going to be a stretch horizontally by a factor of 1/C. Okay? So let me show you what that looks like graphed now, because I think it'll make more sense if I graph it for us. All right, so what I'm going to do here is I'm just going to graph the absolute value of x. All right, so there's our parent function right there. Now we need to compare this with that of 1/2 x. Oops, sorry. There we go. And notice in the picture here, all right, this is not like, I think the easiest way to describe this is look at the slopes. The slopes for the blue, for the parent function, is steeper than the green function, which is our translated function. In other words, what you did is you took all these points, like right here. Let me plot our points here real quick. So we had, I'm just going to plot them real quick. I'm going to pause the video and then plot them and come back. Okay, I'm back. So I went ahead and graphed this, and I want us to just focus on this. So in blue is our parent function. Now, I'm going to go ahead and click on this button over here, and the green stretched function is going to occur. So when you look at this, it's really easy to see that the blue forms this like 90-degree angle, okay, in between. If you look at the green angle in between these two legs here, notice that it's stretched. It's no longer 90. It's bigger than 90 degrees, okay? So that's what we mean by a horizontal stretch, okay? And then finally, if you look all the way down here in the lower left-hand corner, I have the absolute value of 2x. So according to our chart, this is going to compress. It's going to make that 90-degree angle in the parent function even smaller. All right, so watch what happens here. So there we go right there. Notice how it's definitely like an acute angle, no longer that 90-degree angle. Okay, so that's what happens here with this horizontal shrinking and horizontal stretching of graphs. So if I gave us like a really just very dry example here, nothing too fancy, in other words, I could give us something like this and say, okay, given 2 times f of x plus 5 minus 1, identify the translations. Okay? Now, remember, we do have those 5 steps. So let's go ahead and let's look at those steps. So step 1. All right, what's our parent function here? So if I look at this, because the x is raised to the first power, our parent function is linear. Okay? Now, number 2, we're going to be concerned with any reflections about the x or y axis. So if I look at this, I definitely have no reflections whatsoever. So you just put none. 3, we're going to talk about shifting, vertical or left. So vertical, I'll say yes. Down 1 unit. And then horizontal, we say yes. Left 5 units. And then 4, do we have any vertical or horizontal? So I'm going to write them both. Vertical or horizontal. Stretches or shrinks. Okay, well, if you look out front at this number 2, we know that no matter what, that is going to increase our function very dramatically. So we're going to have a vertical. So you can put an X through the horizontal. We definitely don't have a horizontal shift at all, or stretch or shrink. It's going to be vertical. And we'll say it's a vertical stretch by a factor of 2. So that's basically it. Like, it's just being able to identify what you have and then where is it moving from there. So if you really wanted to, you can just look at this. Here's our parent function, which is a linear function. Notice the origin would be like that focal point. Now, according to my steps here, step 1, linear, check. Reflection, none. Am I going to shift this vertically? Yes, I'm going to go down 1 unit and then to the left 5 units. So in red, I'm just going to identify those shifts. So down 1 unit and then to the left 5. 1, 2, 3, 4, 5. And then I know this is going to be a vertical stretch by a factor of 2. So it's not going to have the same slope. It's going to be much more, I guess, pitched, if you will. And that's basically it. That's how this works. That's how, as mathematicians, we can easily look at a function and go, okay, I know exactly where that's going to be. Or better yet, you got a really good idea what this is going to look like when you graph it. The best thing to do, honestly, would be just to go to Desmos and graph the parent function and then graph the translated function. So in Desmos, remember, you got your parent function. And what I'll do is I'll make this just a dotted line like I did previously. I'll make a black dotted line. There we go. Make it a little thinner as well. Okay, and now we're just going to go ahead and graph our linear function here. So this will be, what was it, 2x, or 2 times a quantity, x plus 5 minus 1. And if I just zoom out here a little bit, there it is right there. And notice it's more, it definitely has more of a slope to it. And that's basically it. I mean, that's as exciting as it gets. What's really cool about this, like I said, it's just the ability to quickly identify what you're looking at. So the last thing we're going to talk about in this section, this is a big section, by the way, is going to be even odd functions. Now, even and odd deal with symmetry. So let me write that down here. So what we're really talking about here is symmetry. Okay? And what we want to know is this symmetric with respect to the y-axis or symmetric with respect to the origin? So real quick, I'm just going to make some highlights here for us. So if we have f is even, then what we say is this right here. All right, now I'll show you exactly how to do this. When I was learning it as a student, I always thought it was like so confusing until I just started substituting in what they want me to. Okay, and it was like, oh, makes complete sense. So if f is even, then f of negative x equals f of x for all x in the domain. What this means right here for all x in the domain is no matter what x value you pick, f of negative x is going to equal f of x. That is called even. Now, f is odd if f of negative x equals negative f of x. Notice that the negative symbol is out front of the function for all x in domain of f. So this is going to be odd. Now, we do have 2 really nice pictures down below, okay, that are going to help us out with this. So notice that the graph of an even function is symmetric with respect to the y-axis. You should be thinking of a parabola. Because notice, if I were to just kind of like cut this right down the middle and just fold it, both sides would be directly on top of each other. Okay? So that's what we mean by symmetric with respect to the y-axis. If you have an odd function, then you have symmetry with respect to the origin. Really easy example of that would be our cubic function right here. Okay? All right? So let me show you how to do this now using these definitions, okay? And then with functions. Because like I said, when I was looking at these definitions as a student, I was like, this doesn't make any sense. But it actually is very simple. So here's our example here. So we want to determine whether the function are even, odd, or neither. You can have that case where it's no symmetry exists. Okay, so here's our first example. All right. So first example is f of x equals x to the fifth plus x. Now, I know this is going to sound crazy, but half your work is already done. In other words, here is f of x right here. So if you come up here, I'm going to scroll back up. If you look at our functions, notice you have f of x right here, and you also have f of x down below. All right? The only difference between these two are going to be this has a positive sign and this has a negative sign. But no matter what, you already have f of x. What we are really concerned with, and I'll write this in red, is what happens to this function if I substitute in negative x. So I'm a big fan, first of all, of putting parentheses and then making your substitution, okay? So that's just me. So I will put parentheses first. Oops, sorry. Then I will substitute in negative x. All right? Now, from here, we know the quantity negative x to the fifth, no matter what the number is, it's going to be negative. All right? In fact, let me just write this like this. So we have negative x to the fifth minus x, okay? And then from here, I can factor out a negative 1. So notice that right here is f of x. All right, that's clearly stated over here on the left-hand side. And now look what you have in front of it. You have a negative 1. In other words, you have f of x equals negative f of x. And according to our definitions above, this is odd. Okay? So x to the fifth plus x is an odd function. Therefore, it should exist, or you should see symmetry with respect to the origin. And like always, the easiest way to do this is to go ahead and get out Desmos. So here's Desmos, and I'm just going to type in x to the fifth. Oh, if it'll let me type it in. There we go. X to the fifth plus x. And notice I do have symmetry about the x-axis, or about the origin. The easiest way to do this, or the easiest way to look at this symmetry here, is I definitely am going to have the point, let's see, what is that, 1,6, I think? Oh, come on. It'd be nice if you plotted the point for me. Sorry. What in the world am I thinking? 1,2. All right. And then we have negative 1, comma, negative 2 as well. All right. And there's that symmetry right here. Notice that x and y are both positive, and then x and y are both negative there, which is exactly what you would expect it to be. Okay. Now the next example. So our next example is going to be g of x equals 1 minus x to the fourth. So once again, you already have g of x. Half the work is done. What we're concerned with, what is g of negative x? So remember, rewrite, put parentheses, make your substitution, and then go ahead and simplify. So I'm thinking too much. Negative x raised to the fourth power is still going to be a positive x to the fourth. All right? So notice when you substitute in negative x, you still get g of x out front. This, by definition, this is an even function. This is going to look exactly like x to the second when you graph it. So let's go ahead, let's look at it on Desmos. So we got 1 minus x to the fourth. And notice that it is symmetric about the y-axis, okay? It's just reflected about the x-axis, but it's still symmetric. Left and right-hand side, if you were to cut this right down the y-axis and fold it in half, those halves would sit right on top of each other. Now, obviously I did one that is odd. I did one that's even. I think you can guess what this last one is going to be, which is going to be neither. But let's just go ahead and let's look at it. So let's see here. We got h of x equals 2x minus x squared. So half the work is done. Let's get out the red marker. Let's substitute in a negative and see what happens. All right, so put my parentheses first. Then I make my substitutions. 2 times negative x, well, that's going to be negative 2x. Negative x to the second power, no matter what, is going to be positive, so it remains the same as minus x squared. And then what I could do here is factor out a negative 1. And then when you look at this, it's definitely not even. We know that because it has to look the same, and it doesn't. Second, in order for this to be odd, even though you have this negative 1 out front, this still has to be h of x, which it is not at all. This is 2x plus x squared, and you wanted 2x minus x squared. So in this situation, it's not odd nor even. All right, so no symmetry exists. Okay, and that's it. So I will see you in the next video.